we would like to start the second session of the user interface and user experience, so-called UX session, following the first one in yesterday. Session chairs are Reinhard Becher, Daisy, and Norihiko Kamikubota, KK, that's me. So as like other sessions, oral presentations, allocated time is 12 minutes maximum, followed by 3 minutes Q&A. I will notify the speaker at the time of 10 minutes, meaning 2 minutes left. And audience can write questions by Zoom Q&A or Hoover's Q&A, or after the talk, raise your hand in the Zoom application. So our time is really limited. Let me introduce the first speaker, Michael Ekilon. He is a control system engineer working in Max for Laboratory Sweden. His talk title is Atalanta, the no-code web dashboard in production. So please start.
Thank you. Can you see my slides?
Yes,
we can see it.
Okay, thank you. Good afternoon, everyone. Thank you for the introductions. So today I will give you a brief overview about Atalanta and how we are giving to our users a non-programming environment for building user interfaces. I will describe briefly the architecture of Atalanta and its main components, and then I will show you all of you the device panel, and the dashboard, which are the most important views that we have. And I will finish with some lessons learned and conclusions. But before everything else, I need to give a bit of background. Atalanta started in Max 4 in 2018, and at that time it was still called WebJive. But shortly after, we joined a force together with SKA organization, and we started developing this tool together. And there was a voting recently, or a few months ago, and we decided to rename Atalanta, the whole suite of software. And needless to say that today is in a very active development phase. So the main components of Atalanta are these ones. I mean, on one hand, we have the Tango GQL, or the GraphQL interface on top of Tango. And with this interface, the query or the user interface explicitly asks for what it wants. In this small example, on top right corner, you can see an example of a query where we ask on a particular Tango device, on a particular attribute, a set of fields that we want to get, a set of parameters that we want on the response. All of these parameters are optional, so it's up to the user interface or the requester to select the one that is interested on. So a query returns only the data you ask for. There is also a mutation in GraphQL, so you can, or we can write into Tango attributes, and also we can execute commands. And finally, there is the subscription mechanisms. And in this case, Tango events are linked to WebSockets. So the user interface gets periodically or on change events updated values on every attribute. If the subscription mechanism fails, we fall back to a pooling mechanism. And on the other hand, we also have the Atalanta application itself, the UI. It's built on React and programmed in TypeScript, and it's a single-page web application that contains in the same application both the device panel and the more complex dashboard. And another two main components of Atalanta are the authentication mechanisms, which today supports user and password in JSON files, as well as that authentication. And as a rule, any user, any non-authenticated user can view everything. I mean, can access devices, can run dashboards, but in order to perform actions, you must log in. And by action, I mean writing into attributes, executing commands, etc. And we also have a MongoDB database where we store all existing dashboards in JSON format, and every dashboard is linked to a user, but they can be shared with other users, and they can grant the permissions to different groups in your organization. At the bottom of this page, you can see a link to a GitLab or a GitLab page, and this repository contains quite useful README where with a few commands you can load and set up a whole Taranta suite in your own machine. So just please give it a try. Regarding the views in the Taranta application, the first one that we developed was the device panel, and it follows kind of the same philosophy as the monitor interface in Jive for the ones that know Tango. And it basically recreates the UI based on what the Tango device exposes. So we will see here all the available attributes of a Tango device, the same for properties, commands. Here you can read and write the properties of the Tango device, you can write into attributes, etc. And the attribute values get the updated values via the WebSocket that we mentioned earlier. And if you want to go a bit further in testing, you can check the URL at the bottom, and we have a full demo environment available for all of you. But the most important application that we offer to our users is the dashboard. This is our flagship tool. And what we offer our users is just an empty canvas. We give them complete freedom for making their user interface as they like. Basically, they log in and they can start by dragging and dropping. They can start building the interface almost immediately. The same UI or the same view is used for configuring and for running the interface, which is very handy. It's very handy. This brings, or an important benefit of this is that there is no delay between building the user interface and actually using it. There is no code involved. The users do not need to code absolutely nothing. And there is no software development or software developer involved in this chain. We let the users do their own UIs. And for that, we currently provide 25 different widgets. But of course, we have more under development. They mostly deal with Tango attributes, like read and write attributes. Sometimes we combine several attributes into one widget. For example, for a motor, we can execute commands. We can plot attribute values of different data types. We also can show the state changes on a Tango device over time, etc. And even maybe the user do not care how the widgets are created, but I would like to mention that creating a new widget is reasonably easy. The most basic widget, it only requires two files, a configuration file, which mostly describes the styling of the widget itself, like size and some colors, and the inputs. I mean, the different number of Tango attributes that the widget required, for example. And from that, there is also a React component to be developed, but the Taranta application itself takes care of propagating the Tango attribute inputs into the React props. So that's pretty handy. And of course, this is the most basic widget, so it's up to you if you want to extend the functionality. And there was, during the Tango workshop last week, there was a very interesting demo gave by Jim Link. So please check it out if you want to see how one interacts with the dashboard, how to create new dashboard, etc., and more details about the available widgets. as some conclusions, I mean, the core development of Taranta requires important knowledge about web development. You need to know React, you need to know Redux and all these libraries. But creating new widgets doesn't require that much of a knowledge. I mean, we have people with very little background in web development that were able to create new widgets. I would say that today the process is quite streamlined. And in regards of our users or our user community, there was somehow a slow adoption in the beginning. There could be several reasons. One maybe is because this was web. Our users were not used to web tools, so why change if they already have desktop applications doing the job? And also in the beginning, we have a lower number of widgets. But thanks to the early adopters and their feedback and their request, the number of widgets, the stability, etc., was improved slowly. And today we have a pretty stable and big user community.
Okay,
regarding, yeah, thank you. In general, it's very fast to get a user to start with Taranta dashboard. I mean, a few minutes showing them how it works, it's enough, and they start creating their own widgets pretty much immediately. These are a few examples of several dashboards. Please check the paper for more details and more examples. And I'm finishing with this. For the future, we know that we still need to work on more widgets that have been requested. We would like to improve. We implement a widget of widgets where the user can drop different other widgets and create a composed widget. We need to improve the image handling. Today, it's absolutely not optimized. We are working on bringing a synoptic into a dashboard, widget library, etc. And of course, bug fixing and improvement that are always needed. Yeah, I'm done. Thank you all for your attention on behalf of the MaxID and the Scale Observatory Taranta teams. Thank you.
Okay, thank you very much. So I am looking for a few questions. One from Zoom. The drawing canvas that you expose to the users, is that provided by React, or is it part of your suite?
This is developed by us, developed in React, but this is part of the Taranta suite.
Then, yeah,
it doesn't adapt very well to mobile screens. The device panel, yes, more or less, but the dashboard, no. It's not aimed for mobile screens. Maybe it's something to improve in the future, but today it's not very well suited.
Okay, next question is, how does a dashboard adapt to mobile device screens?
Yeah, I mean, it doesn't fit very well to mobile screens today. The device view, yes, which will be this one fits quite okay, but the dashboard, no, it's not designed for that.
Okay, one, yeah, you can say more. Okay.
Yeah, I mean, yeah, I can answer the chat a little bit more. Yes, React Bootstrap, and well, the strategy. I'm for MaxID, so I cannot answer this question from SK organization, so I cannot answer that one. Sorry, Chris.
Okay, so there are some other, but I will pick up one. What is your strategy at scale for GUI applications in general? Moving everything to this platform or mixing with desktop applications?
Yeah, I mean, I'm sorry, I cannot answer that. I belong to MaxID, not to SKO, so I cannot say that on their name. I'm sorry, Chris.
Okay. So I can find some more questions, but please ask directly to him later. So Reinhardt, to go to next speaker.
Okay. Hello, everyone. So for our next talk, we will have two speakers, a combined presentation. The first speaker of this presentation is Giacomo Strangolino from Elettra Synchrotron Radiation Facility in Italy. He is an assistant professor in fundamental principles of computer science. He's in charge of developing applications and libraries to interface a control system with a control room graphical user interface. And his co-presenter is Lucio Sambon. He is a software developer for web interfaces. So Giacomo, please, Mikel, please stop screen sharing. Yeah, okay, and now our colleagues from Italy, please share your screen.
Good afternoon, I'm Lucio Zambon. I will start saying that this is Canon 3 and it's part of our web framework. And the project is Puma, and his characteristics are reliable, secure, scalable, user-oriented design of multi-platform framework. Our history starts in 2006 till now. We are still developing, and I start to speak about the service. It must be reliable. So regardless whatever happens, if a machine has a breakdown, the whole system should continue to go on painlessly. There is a problem with WebSockets because they don't do load balancing. So if a server breaks down, all the traffic of that server isn't automatically redirected to other servers. So we use another event stream channel. Another issue is security. We could have intrusions of denial of server attacks. And this is leveraged by Nginx. Instead, for the events, we use server-sent events, which is a HTML standard opposite to WebSockets. The goal is having a system so strong not to need a VPN. Scalability also, if we have to scale to many servers, using Nginx plus Redis, we can have a factory of many servers all together. This is a schema of Puma. Then we must serve the web, also mobile application, and we serve even desktop application, which are done in Qt using Cumbia and communicates through the HTTP protocol with the server. And we use Nginx and Anchan. This provides our the best choice is server-sent events through this mechanism. And we use also a database called Redis. And this is the schema of the whole system. And I leave the connection to Giacomo Strangolino.
Hello, I'm Giacomo Strangolino. One last crucial aspect of the design is channel multiplexing. We would like to emphasize that end clients reading the same source require just one reader to the native engine. This realizes one trait of the aforementioned scalability and unburdens the control system downstream. Scalability and load balancing are achieved by use of the prototype architecture depicted in this slide. NHANG and Redis add additional scalability to the whole system. In this slide, we represent the design rationale deployment at Electra, where you can see on the right, on the left, you can see the machines involved in the that host the service, and the Postgres database, where a supervisor oversees the working of the entire system. The tests in this slide, we can see that we had performed some tests on load balancing, and the test environment depicted in the previous slide translates into distribution of more than 1,200 readings across six services. And this slide, you can see a snippet of the Nginx configuration, and here you can see what happens in case of service vanishing. The supervisor detects the condition within seconds and distributes the orphan readings among the active services. So here you can see the load redistribution, and which is always performed by Nginx. So here we can see load balancing and test service web interface, which is implemented by Lucio. The close future roadmap foresees massive test conditions. So another aspect of the Puma service is the native clients, the development of native clients. Telegram is another source of inspiration, characterized by its native applications across all mobile platforms, and native a web interface and an open API to create bots and clients. And last but not least, efficiency, security, and privacy. Alongside web applications, we have the Cumbia HTTP module library, allowing desktop application to run unaffected by the supported engine. There is no engine-specific code in the application, and the latter is run within the same command line. Okay, now I leave the floor to Lucio, which will deal with the web client section.
Hello again. I will focus on a few aspects of Puma web interface. The keywords of my talk are responsive, interactive, and customization. Most Puma pages are responsive. The application adapts to every device automatically. On portable device, screen rotation must not frustrate, but rather it should be exploited to increase usability. I will show two examples. The first is a large SVG synoptic developed for vacuum system. In this case, the trick is to show only parts of the system on mobile. In a demo on YouTube, you can see the effect of a wide increase in screen size. The second example is taken from a gun interlock. You can see the same screen on desktop and on mobile. Bootstrap is used to collapse blocks on mobile. The second keyword is interactive. The web interface must react quickly to user actions. For example, users can zoom in and out in SVG synoptic using mouse wheel on desktop and pinch on mobile. New contents are shown depending on the zoom level. Some sources are subscribed and unsubscribed on ban or zoom change. so that only the visible ones and a few side buffers are continuously updated. The JavaScript function which subscribes sources is called at a maximum rate of 2 times per second. This feature is completely transparent to users. A demo is available on YouTube. The third keyword is customization. For common users, the designer produces responsive pages using Flexbox, which is a CSS3 standard. Pages are saved in JSON format in a database. JSON files are interpreted by a web page and by an app. Each saved page can be used as a module embedded in new pages. Instead, for programmers, Puma provides an online HTML editor with the site preview, which is constantly updated. An authorized user can insert any HTML source, which may include JavaScript, CSS, and SVG. The connection to the control system can be implemented in any HTML or SVG tag by inserting a class Puma, a unique ID, and a custom data attribute named data source.
Please note 2 minutes left, please.
Yes, this is a voltage ramp configurator. It is divided in 2 areas. On the left, there is a table of steps. On the right, there is the graphic representation of those steps. You can drag and drop points on the curve, and numbers on the left will change instantly. Ramp configurator is included in an overview of the projector of the booster available on YouTube. And that's all. Thank you. If you have any question.
Okay, thank you very much for your presentation, both speakers. So I'm looking around. Do we have questions from the audience? Presently, I don't see any. Okay, maybe one should look to the chat. Also nothing. QA. Obviously, there are no questions from the audience. Maybe if Mikel is still around, maybe he could answer one question which was left from the last talk. Mikel, are you still available? Okay. There was one question, I guess, left. Have you done any benchmarking? And how many devices can it connect to a single dashboard?
I don't have any benchmark in mind, but we have dashboard with tens, maybe 20, 30 different attributes from different devices. It works okay. The main problem comes if the attributes get updated very often. There we have seen issues like the high CPU consumption and the browser, but it's usually very dashboards that are pretty much overloaded. I don't have a number for you.
Thank you very much. Once again, the question of other question with respect to the second talk, obviously not. Then thanks again to our speakers, and let's move to the third presentation. Norihiko, please.
Yeah. So the next speaker is Xiaohan Xie. She is a graduate student at Huazhong University of Science and Technology in China. And now she's in the International Joint Research Laboratory of Magnetic Confinement, Fusion, and Plasma Physics. So the talk title is a major update of web-based development toolkit for control system of a large-scale physics experimental device. Okay, please.
Okay. Okay. Hi, everyone. My name is Xie Xiaohan from the GTEx team in China. It's an honor to be here to have the chance to speak to a major update of web-based development toolkit for control system of large-scale physics experiment device. And my presentation will be divided into 4 main parts: is introduction, the current states of CFAT, update of CFAT, and application. First is introduction. SCADA is a software tool which is used for the construction of the control system of experimental facilities. For a long time, EPICS has been used to build experimental equipment control systems in the accelerator field. So far, the community has been very mature, and EPICS has very strong support for hardware equipment in the accelerator field. For fusion community, after chosen by ITER, EPICS is used by many toolmarks as well. But the technology used in toolmarks are very different from those in accelerators. So it is not a straightforward job to create EPICS support for equipment used in fusion community. In response to this situation, we propose CFAT. CFAT is a SCADA that proposed an abstract model for control system and a framework that uses web technology to build a control system. Based on web technology, CFAT will also supported by everyone and also provides stronger support for new devices. Before I talk about the major updates of CFAT, I'd like to talk about the basic concepts and the current status of CFAT. The basis of control is that every client in this system can understand each other conceptually. So we have to encapsulate the equipment in control system into a common model. We abstract all the objects to be controlled into things. A thing can be either physical or logical. Now, the main communication model of CFAT uses the HTTP protocol of the RESTful architecture as the basic transmission protocol. The format of the RESTful framework is to use URI to locate resources and add verbs in front of the URI. Currently, CFAT has still many functions and components that need to be improved. A CFAT application, in principle, is allowed to mount multiple communication models when accessing resources. You can choose communication model via the protocol header. But the communication based on HTTP can only be initiated by the client. This one-way request feature determines that if the server has continuous state changes, it is very troublesome for the client to be informed. We can only use polling. Instead of polling, CFAT is a property. Event is a property of CFAT that others can subscribe to and get notified on a certain condition. CFAT is based on WebSocket community models. We have this model before, and this time we improved support for cross-domain events as well as added support for WebSocket on the front end. Okay. Sorry. The WebSocket-based event also has some problems, such as a client or server going offline or package lose during transmission. The MQTT is a protocol designed for communication between a large number of remote sensors and control devices that have limited computing power and work on an unreliable network. Provide one-to-many message publishing, decoupling subscriber from publisher. The decoupling has several dimensions. Publisher and the subscriber do not need to know each other and do not need to run at the same time. MQTT also has 3 message distribution qualities of service. CFAT MQTT's communication model still uses RESTful architecture. The only difference from HTTP is that you need to replace HTTP in URL with MQTT to select MQTT communication model. MQTT is currently widely used in the IoT and is supported by multiple clients such as Node-RED. Node-RED can also be used in CFAT. Okay, I'd like to move on to talk about HMI. In web-based control system, all HMI is a website running on web servers. A HMI can make a request to any CFAT host. When the CFAT host receives a request, first, the CFAT web server find out the request is from the browser. It will redirect the browser to the HMI location with a hash fragment indicating the resource the user wants to access. But if the response is not the HMI, the browser will try to get the resource and use the resource to generate a suitable widget. The HMI is composed with reasonable components called widget. CFAT pros a component called widget UI. The application developer can compose their own HMI while adding and dragging widget. Users can enter the editing interface where you can fill the resource UI you need to access and can also choose some style selections and function configuration. The component library of widget UI provides many widgets such as label, configurator, gauge, video player, switch, state light, and so on. The interface can be saved as a JSON file, and it is also supposed to subscribe a remote event through WebSocket protocol, which you can be done by simply clicking on the website. Okay. Researchers often need to constantly adjust the experimental process, so the process control needs to be dynamic. CFAT introduced the state machine, which can be written with a simple configuration file. The user can construct their own state machine by writing all the states, the condition of state transition and action to be executed in the configuration file, and can change them at any time. Engineering data refers to the no experimental data generated during the experiment, such as sensor data. Most of them have strong timing characteristics. CFAT uses InfluxDB to store and monitor engineering data, which is capable of ingesting millions of data points per second. In CFAT, we still write the control of InfluxDB as a thing with I/O interface exposed. And in addition to this, a dashboard interface and monitoring alarm interface built with Grafana are also used in CFAT to realize the engineering data. And Docker is an open source application container engine that allows developers to package their application and dependency package into a portable container and then distribute to any popular Linux or Mac or Windows machine. CFAT uses Docker-based policy deployment to run simply in CFAT application quickly. The compatibility of CFAT with ePICS is also greatly improved. Using our Docker image and ePICS IOC can be run very quickly based on a simple configuration file. The user do not need to know how to build the ePICS server. Through the CFAT client, this thing can easily read and write PV. If the value of PV changes, it will publish a CFAT event also. Well, let's talk about the application of CFAT in the end. The field reversed configuration device, also called FRC, is a new type of fusion research device proposed in recent years. HFRC is a FRC device being researched by Huazhong University of Science and Technology. HFRC chose CFAT to build his control system. With the CFAT framework, each subsystem can know any message from each other. And the central control system can coordinate and monitor by obtaining the status of each subsystems. The HFRC control system is divided into two parts, the global control system and the sub-control system. The global control system coordinates sub-control system to meet the control requirement. The control system also uses dynamic state machine to realize the process control of the discharge. Okay, that brings me to the end to my presentation. Thank you for your attention.
Thank you very much for keeping time. So now talk is open for questions. So far, I cannot find, even in Hoover side, I cannot find any questions.
Okay.
So may
Maybe-
I ask, what you
Maybe
asked?
maybe I can ask the question if.
Mhm.
How many devices are controlled by your system? How many?
Actually, we haven't focused on this. In principle, CFAT can communicate with any devices, and in FRC, maybe there is 30 to 15 devices in there.
That's good. So I also want to ask, in the just you show some editing functions, and I want to know what kind of widgets are available with this CFAT.
With this what? With this
With
sequence?
this one.
With this one.
Yeah, yeah. So yeah, this page. Just I
About-
can see meta, buttons.
Yeah, there's labels, status light, switch, button, gauge. It's about maybe 15 widgets.
Okay, thank you.
Okay.
So I am still waiting some more questions. Oh, just to wait a moment.
Okay.
Do you use InfluxDB 2.0? What is the throughput you have here?
Yeah, yes, the CFAC is improved to the InfluxDB version, the 2 point. I don't sure I understand what you're asking.
What is the throughput? Throughput, how fast or how slow?
How fast or how slow? About InfluxDB to store data points. It's about millions of data points per second.
Okay, so now it's approaching the time. Thank you very much.
Okay.
I see one additional question, if possible, in Huwa. There is one question more. Is the source code public?
Yeah. We upload our application on the GitHub, and it is open resource.
Okay, thank you. Good, then let us move to our last presentation. The presenter is Georg Weiss from the European Installation Source in Sweden. Georg is a software developer. He is responsible for the development and the maintenance of the control system UI based on Control System Studio, and here on the variant Phoebus. And he is also responsible for the various services used by Phoebus. So please, Georg, share your screen, and the stage is yours.
Thank you very much. I hope everyone can hear me. I will try to run this in presentation mode. So this is about Phoebus OLog. I'm sorry to disappoint anyone who was expecting any more talks about web frameworks. To give you some background, Phoebus is basically the latest iteration of Control System Studio. And Control System Studio in turn is, and I quote here from the website, that is a collection of tools to operate large-scale control systems. And in this case, Control System Studio means it is not the control system per se, because it's basically only the front end, the UI front end of a control system, which is in practice epics. Now, the original implementation of CS Studio was based on Eclipse, A few years ago, the community behind the Control System Studio decided to abandon Eclipse in favor of Java and JavaFX. So Phoebus is the name of that project, and we have adopted it to be synonymous with Control System Studio in its latest version. What you can see on this slide is a non-exhaustive list of sites using Control System Studio. There are, I'm sure there are more. Of these sites, it's ESS, where I work, that is using Phoebus. The other sites are transitioning. Other sites are transitioning to Phoebus from Control System Studio, the Eclipse-based Control System Studio. Now, what is OLOG then? OLOG is, in short, a digital logbook, which is needed for many things in a facility like ESS. It supports creation of log entries to which you can attach metadata and attachments, basically files. It supports searching for log entries. It supports authentication so that only authenticated users can create log entries. Anybody can read log entries, but the creation of log entries should be controlled. The OLOG is integrated into Phoebus, but there are other clients. There is a web-based client or a JavaScript-based client for the web. And there is an OPI, an API. OLOG is both a service and two clients, the Phoebus clients and the web clients. The service exposes an API so that any client can access the service and create and read log entries. Now, what is the driving factor behind this project that we call Phoebus OLOG? Well, in Brookhaven, there is a legacy version of OLOG that has been used for about 10 years. It is integrated into the legacy version of CS Studio, but it is considered very difficult to maintain, and it does not scale well. At ESS, we are using eLog. We have been using eLog for 5 years. That's a logbook that is currently maintained by PSI in Switzerland. It is very rich in features, but we find it very difficult to customize and maintain. And we also want to integrate the electronic logbook or the digital logbook into CS Studio, into Phoebus, and that is also very difficult with eLog. So these are basically the driving factors. So we have this joint project to create Phoebus OLOG. It's Brookhaven, it's ESS, and we have also contributions from Argonne in Chicago. Now, what does it look like? Well, I'm showing you here you see a portion of the log entry editor as it looks in the Phoebus client. The user is supposed to provide credentials and some metadata. Some of these fields are mandatory, some are optional. And once those details have been specified, the user can write a body to the log entry. And we discussed for a while how to support some kind of markup so that we can have a bit of styling in the log entry and support for other things like images and tables. And we arrived at the conclusion that we should use a reasonably simple and well-supported markup solution, and that is Common Mark. Common Mark is well defined, well specified, and has support in many languages, and is, by the way, also used by GitHub. So it's not a unfamiliar technology. To the right, you can see what the log entry is looking like, the body of the log entry, how it's edited. And to the lower right, you see how it comes out in a viewer. We also support embedding of images into the body text. What you can see here in marked in red is how to write, how to use common mark to embed an image. It's quite difficult to do this by hand. So we have in the editor, we have tools. The user can press a button and select a file from the file system, specify the size of the image, and that will be embedded automatically into the body text. Now, in Phoebus, the user can launch the editor by a toolbar button, but there's another alternative which demonstrates how it is integrated, how OLOG is integrated into Phoebus. When using an OPI in the control room, the user can right-click to launch the context menu. You see a portion of that to the left. And from the context menu, the user can select Create Log, and that will launch the log entry editor and automatically also attach a screenshot of the OPI from which the context menu was launched. The screenshot will be attached to the log entry. The same is possible in the Phoebus application called the Data Browser, where the user can right-click on a plot and create a log entry from that. What you see to the right is that will automatically attach two things: a screenshot of the plot, which is not shown, but also the PLT file, which is a Phoebus specific thing that you can open in Phoebus to actually see the plot, if you like. On top of the metadata and the attachments, there is also support for something we call properties. And a property is a named list of key value pairs. Each site can configure this according to their needs, but a property is basically something that is, for instance, shift information or experiment information. Those properties can be added manually by the users, or if you implement it that way, they can be automatically added to each new log entry. There is also support for something we call grouping, which is basically a lightweight thread, if you like, where a user can reply to a log entry and then in the viewer see them grouped as a parent entry to the right, to the left. You can see the parent entry on top and the replies to that entry. In this manner, a type of conversation can be rendered in the UI, so that log entries that logically should be grouped, they can be rendered as a group. To actually see the log entries, well, I've mentioned that there is support for search. And the search is based on Elasticsearch, which is a very flexible and fast search engine.
2 minutes left.
Thank you. And the search will basically define the filters that you want to in order to find your log entries. I mentioned the Phoebus client. There is also a web-based client. It's implemented in React and React Bootstrap. The same view is in Phoebus will look like this, where you have the search result list to the left and the actual log entry to the right. To the right, you also see how an embedded image comes out when you embed it into the body text. We also have something called notifiers. When a new log entry is created, applications can be notified about it. We have integrated this into a mobile application so that anyone installing this can see that a new log entry has been created. These mobile applications, we have one for Android, one for iOS. They are developed by ESS, and the Android version is available on Google Play. Now, the interesting thing about the architecture is that OLOG is the service side is based on Spring Boot. It's using MongoDB for attachments. It uses Elastic to store the actual log entry. And we also get the search capabilities for free. The project also includes the Phoebus client and the web client, but other clients are of course possible. And this is by no means Phoebus specific. This system can, or this framework can be used for any application. In the project on GitHub, we also provide Docker files if you want to containerize this and get started quickly. In the presentation here, we have added some links as well, if you want to read more about it. Any questions? Thank you very much.
Thank you very much. So we have time for a few questions. I already see questions coming in. There is a question concerning web client. If you have a web client, why do you also need to have a Java client or vice versa?
Well, the Java client in Phoebus integrates, for instance, with the OPIs and the data browser. So we think it's a very convenient way to create log entries and get, like, for instance, screen shots for free. And the viewer in Phoebus also, this is on our backlog, the viewer in Phoebus will also be capable of launching those OPIs that have been attached as references in log entries. So we see the Java client as an integration with Phoebus. The web client is needed because not everyone will take the trouble of installing Phoebus, or they might need to look at log entries in their mobile devices.
Okay, there's another question. How does the Java FX change of support policy from Portal affect your future plans?
Yeah, I don't have a good answer for that. We will just need to hope for the best.
Next question, do you provide any packages like RPM?
No, we don't. For the Phoebus project, we have some instructions on how to build Mac and Windows installers. We have tried the similar approach for Linux, but that has not been turned out well. That simply doesn't work. I don't know why, and I have not spent time investigating that.
Maybe there's more time for one additional question. I look to the chat. Is a logbook filled only manually? How it is coupled to the control system or experiment?
Not sure what the question is, but that is all. There are APIs available, so any site can integrate to whatever needs they have. At ESS, we integrate currently we only integrate the shift information into the logbook entries automatically. But we have discussed other solutions and other approaches as well.
Okay, so unfortunately we are approaching the end of our session. There are a lot of more questions in Zoom and also in the Hoover Q&A. So I would propose that all questions which have not been answered, please put it to the Whova Q&A so the speaker can respond also offline and answer your question. So thank you.
I will not be able to answer them right now. I can answer them later tonight.
This, I guess, also will work. So we are at the end of our session. Thank you very much to all speakers again, and also to the audience for listening and for raising the questions. Okay, bye-bye.